Hey there, Professor Brown here, and in this video we are going to talk about how we fill electrons into their atomic orbitals. Here in the picture you can see a depiction of the quantum mechanical view of the atom. On the first energy level we see the yellowish looking sphere as the 1s orbital. The first energy level only has the s orbital. It doesn't have any s or p orbitals, or rather p, d, or f orbitals. And so therefore that is the entirety of the first energy level, the 1s orbital. As we move to the next energy level, the 2 energy level, we see that the 2 energy level includes both an s orbital, that is the grayish looking sphere, as well as p orbitals, the red dumbbell shaped orbitals that you see that are somewhat bigger than that first energy level. That is the entirety of the second energy level, and all of those are a little bit higher in energy than the s orbital on the first energy level. So we will talk about how in larger and larger atoms what orbitals the electrons are placed into as they fill into the atom. There are a couple of rules and principles that can help guide us along the way. First of all, electrons are placed into atomic orbitals in a specific order. The lowest energy levels are filled first. This is what is known as the Aufbau principle. Each atomic orbital can accommodate a total of 2 electrons. These electrons must have something known as opposite spins, and we will look at that a little more in depth in a little bit. For right now though, just know that every atomic orbital can occupy a maximum of 2 electrons. Finally, as we are filling our atomic orbitals, we will come to some spots where we have more than one orbital at the same energy level. This might be the case with, for say, the 2p orbitals that we see here. There are 3 of them, but they are all at the same energy level. We half fill orbitals at the same energy level with 1 electron before we go back and double up to fill 2 electrons into any, as we say, degenerate orbitals. On the next couple of slides, we will take a look at a few of these rules in a little bit more depth, and then we'll do some practice filling atoms with their electrons.
Now you might be thinking to yourself, that seems simple enough. I can fill up these orbitals in order 2 by 2, no problem. Well, there is somewhat of a problem. The order in which the orbitals are filled is not as straightforward as one would hope when you get to atoms large enough to contain the d orbitals and the f orbitals. D and f orbitals on one energy level are often higher in energy than s and sometimes even p orbitals on subsequent energy levels. And so the ranking of the total energy of each orbital is not quite as straightforward as you would think. For example, here we can see kind of what we're talking about. If we look at this 5th energy level here, we can see that the 5d energy levels, or orbitals rather, are actually a little bit higher in energy than the s orbital on the 6th energy level. And so that presents us with a little bit of problem figuring out what the ranking order is of the energy of every orbital. We'll see a diagram on the next slide that will hopefully help you keep these orbitals rankings in line.
So here on this slide we see a chart, or a diagram rather, that helps us keep the atomic orbitals and their filling order to be remembered. And you may be thinking to yourself, Mr. Brown, how do I remember to draw a diagram like this? It just seems like orders with or symbols and letters with some arrows through it, and that seems kind of convoluted to memorize. Well, it's not actually that tough to memorize. Let me show you the way I can construct this chart on my own without or from memory rather. What I usually do is I start by writing the numbers 1 through 7 in a column. 3, 4, 5, 6, 7, as you see there, and then start another column that goes 2, 3, 4, 5, 6, 7, then a third column with the numbers 3, 4, 5, 6, and 7, and then a fourth column with the numbers 4, 5, 6, and 7. And then you write S's down the first column, P's down the second column, D's down the third column, and F's down that fourth column. And then you kind of think of this as somewhat like a grid. You don't have to draw the lines as you get more used to constructing this diagram, but lines may be helpful at first. And we are going to run arrows through the diagonals of every one. And following from the top to the bottom of every arrow will result in the filling order, the correct energy filling order of all of the atomic orbitals. So the correct filling order for the atomic orbitals is as follows. You start at the top here and we follow the arrow down. The first one we fill is the 1s orbital. We go to the top of the next arrow here and follow it down. The next orbital we fill is the 2s orbital. We start at the top of the next arrow. We fill the 2p orbital. Then we fill the 3s orbital. We start at the top of the next arrow. We now fill the 3p orbital followed by the 4s orbital. 3p, 4s. Then we start at the top of the next arrow. We see that 3d comes after 4s, and if we look at the diagram on the previous slide, we would see that the 3d orbital is a little bit higher in energy than the 4s orbital. After the 3d, we see the 4p orbital is filled next. After the 4p, we see the 5s orbital is filled next. Then we would move to the top of the next arrow. After 5s, we fill the 4d orbital, followed by the 5p orbital, followed by the 6s orbital. If we follow this trend by following the arrows, we can outline the energy rankings of all of the atomic orbitals. And all we have to do is remember to write 4 columns, 1 through 7, 2 through 7, 3 through 7, 4 through 7, and then put S's on the first column, P's on the second column, D's on the third column, and F's on the fourth column. Drawing arrows moving diagonally downwards and to the left through each diagonal will result in the correct atomic filling order. So here we see the first type of diagram we are going to look at to understand where electrons are residing in an atom. These are known as orbital diagrams, and in orbital diagrams we represent our electrons by drawing half-head arrows in these boxes that represent the atomic orbitals. You can see that there is 1 box for each of the s orbitals and 3 boxes for the p orbitals because there are 3 p orbitals. There are 5 boxes for the d orbitals because there's always 5 d orbitals, and those f orbitals have 7 boxes. We place these half-head arrows in these boxes. Some have to be pointed up to represent an up spin on an electron, while others have to point down to represent a down spin on an electron. And any electrons that share a box must be opposite. And then electrons are always placed in unoccupied orbitals at the lowest energy level first, and that's what we learned in the previous slides talking about the Aufbau principle and Hund's rule, and we'll take a look at how that works on the next couple of slides, filling up our own orbital diagrams. Here's the first example of an orbital diagram we will draw ourselves. We are going to determine the orbital diagram for a neutral atom of nitrogen. We have the periodic table inset for nitrogen here, and we can clearly see that nitrogen is atomic number 7, which we now know means that a neutral atom of nitrogen has 7 protons and therefore will have 7 electrons. So we're going to fill these electrons into the correct orbital using the rules we discussed on the previous slides. The main rule is the lowest energy levels go first. So The 1s orbital is the lowest orbital in energy we have, and every orbital we can hold 2 electrons. So we're going to put 2 electrons in that orbital. We're going to show one with an upspin by pointing a half head arrow up, and we're going to show another with a downspin by pointing a half head arrow down. So we put 2 electrons in the 1s orbital. The next orbital in energy level order is the 2s orbital, and that 2s orbital will also be able to hold 2 electrons, one with an upspin and one with a downspin. That puts 4 electrons total in their correct orbitals. We have 3 more we need to take care of. The next orbital, or set of orbitals rather, in energy level order are the 3 2p orbitals. We maybe have a decision to make here. How do we fill the 3 2p orbitals since they all have the same energy, something we call them being degenerate with each other? Meaning, should we put 2 in the first box followed by 1 in the middle box, or should we put 3, 1 each in each of the 3 orbitals? Hund's rule says we should half fill our orbitals before going back and doubling up, so we will take option B, where we put 3 electrons, typically all shown with upspin, in the 3 degenerate p orbitals at the second energy level in order to half fill them instead of doubling them up. This shows us the correct electron configuration for a neutral atom of nitrogen. Here we have example number 2. We are going to attempt to draw the orbital diagram for a neutral atom of magnesium. Magnesium is atomic number 12, so in a neutral atom we would expect 12 protons and 12 electrons. We start, as we did earlier, filling the 1s orbital with 2 electrons, opposite spins, the 2s orbital with 2 electrons with opposite spins. That takes care of our 4 electrons, our first 4 electrons. And we talked about how the 2p energy levels are next. So we can fit 1, 2, 3, 4, 5, 6 electrons in those 3 2p orbitals. That takes care of a total of 2, 4, 6, 8, 10 of our 12 necessary electrons. So we have 2 more left to fill. We see in the orbital energy order, the next lowest orbital is the lone 3s orbital, and we have learned that every orbital can hold 2 electrons. So I will place my final 2 electrons in that box, giving me the correct orbital diagram for a neutral atom of magnesium. Now we will attempt a little bit more complicated example, only a little bit more complicated because we have a good bit more electrons for our neutral atom of iodine. Iodine is atomic number 53, so it's going to have 53 protons and therefore 53 electrons in that neutral state. So we will start with the 1s orbital as we have done so far. We will put 2 electrons in that orbital, 3, 4 electrons in the 2s orbital, 5, 6, 7, 8, 9, and 10 electrons fill up to the 2p orbitals, 11, 12 in the 3s orbital. The next orbital in energy are the 3p orbitals, 13, 14, 15, 16, 17, 18. Next, we move to the 4s orbital, 19, 20, followed by the 3d orbital, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. The next orbital in line is the 4p orbital, 31, 32, 33, 34, 35, 36, followed by 5s, 37, 38, followed by 4d, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, followed by 5p, 49, 50, 51, 52, and 53 electrons, gives us the correct electron orbital diagram for a neutral atom of iodine. So we will take a look at how we often write out our electron configurations instead of always drawing these orbital diagrams here on this slide. We are going to take a look at the electron configuration and orbital diagram for a neutral atom of sulfur. And in a neutral atom of sulfur, we have the atomic number 16 representing 16 protons and therefore 16 electrons in a neutral state. So we will fill in these electrons on our orbital diagram as we already have done. Let me zoom in a little bit so we can see it. We have 1, 2 electrons, 3, 4 electrons, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electrons. And so we can see what the correct orbital diagram looks like for a sulfur atom here. But a lot of times when we're writing a paper and we want to talk about the electron configuration of the atom or species in question, we may not have a bunch of room to always give an orbital diagram. And so a lot of times it will be written out with the following notation instead of a complete orbital diagram. And we start with writing the orbital down. We see the 1s orbital has some electrons in it, and to be specific, it has 2 electrons. And you see the number of electrons go in a superscript position above the orbital that you are designating. So the 1s electron, or the 1s orbital rather, has 2 electrons. The next orbital that we see that has some electrons in the energy order is the 2s orbital. So we write 2s, and it also has 2 electrons. So the next orbital that we come to is the 2p orbital. And we can see that in the 2p orbitals, there are 6 total electrons. And so when we're condensing these electron configurations down a little bit, we just typically write the total number of electrons in that superscript position. Rather than indicating there are 3 separate orbitals there, we kind of assume the reader knows that. So 2p6 comes next in this sulfur electron configuration. The next orbital that has some electrons is the 3s orbital, and it has 2 electrons. And then we see the final orbital that has some electrons are the 3p orbitals, and they only have 5, so we will write a 5 in that position. So this is the correct electron configuration for sulfur, and you can read it: 1s2, 2s2, 2p6, 3s2, 3p5. Here we're going to write an electron configuration for silicon, which is atomic number 14, and therefore we'll have 14 electrons in the neutral state. We have a periodic table here that shows which orbitals are being filled for which element, and you may start to recognize some of the patterns in these electron filling orders as you start to practice and get comfortable writing these electron configurations. We know we have 14 electrons to fill, and we know that the first atomic orbital, the lowest one in energy, is the 1s orbital, and it can accommodate 2 electrons. The next atomic orbital in energy level is the 2s orbital, and it also can accommodate 2 electrons. The next atomic orbital that is in the energy level ranking is the 2p orbitals. The 2p orbitals each can hold 2, but there are 3 of them, so there are 6 total electrons held by the 2p orbitals. The next orbital that we fill is the 3s orbital, and the s orbitals can hold 2 electrons. And as we move towards silicon now on our periodic table, we can see that we are only filling 3p with 2 electrons. So the 3p orbitals will get 2 electrons, and that should all add up to 14. 2 plus 2 is 4, plus 6 is 10, plus 2 should be 14 total electrons. So the electron configuration for silicon is 1s2, 2s2, 2p6, 3s2, 3p2. Here, in this example, we will write the electron configuration for a neutral atom of zirconium without using a periodic table. We're only going to use an Aufbau principle arrow chart here to help us determine this electron configuration. We know a neutral atom of zirconium is going to have 40 electrons due to its having 40 protons according to its atomic number. And to use the Aufbau principle arrow chart, what we do is we start at the top of the first arrow that we see and we move down through the atomic orbitals, and that will give us the correct filling order for the energy levels of the atomic orbitals. The first one is always 1s, and we have learned that s orbitals hold 2 total electrons, and so we're going to fill these up until we have 40 total electrons. We write 1s and we write a 2 there to indicate there are 2 electrons in the 1s orbital. That brings us to the bottom of the arrow, so we go to the top of the next arrow and continue moving down. The 2s orbital is next. S orbitals hold 2 electrons. That brings us to the bottom of the arrow, so we move to the top of the next arrow and continue moving down. The 2p orbital is the next orbital in order. P orbitals come in sets of 3, so they hold 6 total electrons. Continuing down that same arrow, the next orbital we come to is the 3s orbital, and s orbitals hold 2 electrons. That brings us to the bottom of that arrow, so we will move to the top of the next, continue our way down, showing us that the 3p orbital is next in energy level order, and we know that p orbitals hold 6 electrons. Continue moving down that arrow to arrive at the 4s orbital next in order, and s orbitals hold 2 electrons. I'm going to stop there and count my total electrons to get an idea of how many I've filled so far and how many I have left to go. I have so far put 2, 4, 10, 12, 18, 20 electrons into this electron configuration, so I have 20 more left to fill. With that brings us to the bottom of that arrow, so I will go to the top of the next arrow and start my way down and notice that there are, or the next orbital in level is the 3d orbital, and d orbitals can hold 10 total electrons. So that takes care of my 20 that I have left to go. 3d10 means 30 total electrons have been filled. Continuing down that arrow, the next orbital in energy level order is the 4p orbital. And p orbitals hold 6 total electrons. That leaves us with probably 4 left. Let's recheck. 2, 4, 10, 12, 18, 20, 30, 36 electrons left to put in our orbitals, or 36 electrons total that we've put in those orbitals, rather, 4 left. The next one we come to is 5s, but we can only put 2 of those 4 in the 5s orbital. That brings us to the bottom of the arrow, so we will go to the top of the next and move to the d orbital next, the 4d orbital next. D orbitals always come in sets of 5, so it can hold up to 10, but we only have 2 left to place. Quick recount: 2, 4, 10, 12, 18, 20, 30, 36, 38. We're trying to get to 40, so we only need to place 2 electrons in that 4d orbital to get the correct electron configuration for zirconium. There are some elements that show exceptions to the Aufbau principle, particularly some of the transition metals, and these are the ones that I would like you to be aware of. These elements tend to borrow 1 electron from an s orbital to either halfway fill or completely fill the previous d orbital. We'll look at their orbital diagrams and electron configurations to see what we mean on the next couple of slides. Here we see the electron configuration for molybdenum. This entry is from ptable.com, by the way. Now that you've made it this far, I can tell you that if you go to ptable.com and click electrons in the top option bar,
you will see a periodic table that will give you the electron orbital diagram and configurations for all of the elements on the periodic table. But if we look at the electron configuration for molybdenum, what we notice is, and within the orbital diagram, is right here. We have seen the, up to this point, we would expect to fill that 5s orbital before we put this last electron that's highlighted in the 4d orbital. We would expect that electron to be in the 5s orbital. But molybdenum, as explained on the previous slide, it finds itself in a more stable configuration with all of those half-filled orbitals rather than having the last electron in the 5s2 configuration instead. And so the correct electron configuration for molybdenum is 5s14d5 at the very end to signify all of those half-filled orbitals. We also see the same thing with the other elements that I depicted on that slide. Copper, silver, and gold all display this behavior at the end of their electron configurations, where instead of placing 2 electrons in the 6s orbital and 9 electrons in the 5d orbital, instead it places 1 electron in the 6s orbital and 10 electrons in the 5d orbital, because that gives you a half-filled s orbital and a fully filled d orbital, which is a more stable configuration than a full s orbital and then a 1/2 empty d orbital. So it just prefers this configuration, and all 3 of those elements in that column will display that same behavior at the end of their orbital diagrams. And those are the exceptions, like I said, that I want you to be aware of to the Aufbau principle. As I've mentioned a couple times in our lectures and discussions so far, chemists are famous for being lazy. And now I want to introduce you to how we are lazy with our electron configurations. You may notice every electron configuration just changes the last number by 1 as we move up the periodic table. For chemical reactions, we really only care about electrons in the outer orbitals, what we typically call valence electrons. Noble gas configurations allow us to write shorter configurations using the so-called noble gas at the end of each row of the periodic table to represent the core of electrons while writing out the configuration of the outer electrons. It always uses the noble gas immediately preceding the element you are trying to write a configuration for. And I've given you each noble gas's complete electron configuration here, except for the last 2, where we have shown an example of how to use the noble gas configuration to shorten up the written electron configurations. And of course, we will practice a few here on the next couple of slides. So here in this example, we will investigate how the noble gas configuration works by looking at the configurations for a neutral atom of magnesium. And we have the ptable.com entry here showing the orbital diagrams and the what they call expanded configuration. That's what we have called electron configuration so far. And then for configuration, they have the noble gas configuration. And I just want to show you how they arrive at that noble gas configuration. We see that it is neon 3s2. And we see that the total expanded configuration for magnesium is 1s2, 2s2, 2p6, 3s2. And the reasoning behind this is neon, if we were to write out its electron configuration, we would find, and we would see on the previous slide, that it is 1s2, 2s2, 2p6. And if we write out the electron configuration for magnesium, so we just move 2 more down the periodic table in atomic number, we find that it is 1s2, 2s2, 2p6, 3s2. And so chemists, in their infinite amount of laziness, would rather, instead of writing all of this out every time, they just use some brackets, because all of this is basically the same thing. And so therefore, the noble gas configuration for magnesium becomes neon in brackets 3s2.
One final note about electron configurations is it is possible, and you will be asked, to determine the electron configuration of some ions. Electron configurations of ions are done the same way as neutral elements, only with making sure you use the correct number of electrons according to the charge that is shown. The same orbital filling rules will apply. Neutral atoms and ions that share an electron configuration are said to be isoelectronic with each other. And so let's say, for instance, you were asked to write the electron configuration for a sodium plus ion. We know that sodium is atomic number 11. So a sodium plus 1 ion is going to have 10 total electrons. So that means the sodium 1 plus or plus 1 ion is going to have an electron configuration of 1s2, 2s2, 2p6. And we may notice that this is the same electron configuration that we were looking at for of neon. So we say that a sodium plus 1 ion and a neon atom are isoelectronic with one another. Conversely, if we have to do a negative ion like chlorine with a -1, we would see that chlorine typically has 17 electrons, but in the -1 state, it has 18 electrons. And so the electron configuration for the chlorine 1- ion would not be 1s2, 2s2, 2p6, 3s2, 3p5. We would end it in 3p6 in order to show that extra electron from the one negative charge in the chlorine ion. And that brings us to the end of this presentation on electron configurations and orbital diagrams. As always, if there is anything unclear, you have more questions, please reach out to me via email at brownb@sandhills.edu.